I'd like to thank the organizers of DISIO, particularly Pierre Andre, who's in the back of the room. Thank you for getting me to Poland, Pierre. And also I'd like to acknowledge my co-author, Dr. Jan van Ys. Jan, can you stand up? So we'll be talking a little bit about a few general slides about soybeans and soybean meal, talk about the use of soy protein in poultry and monogastric feed, soybean products and soybean meal, and also about a little bit to do with processing and how that affects variability and some other things that also affect variability and what we might do to control that variability in feed manufacturing. How many here are working for a feed company or a company that produces feed? So quite a few. And I think the rest of us are probably in academia. So this is just a general slide showing the global production of and consumption of soybeans since about the year 2000, the last nearly 20 years. This ended last year. And in the red is the production and the blue is consumption, and they're nearly neck and neck. The difference between those is the ending stocks, which if you have small ending stocks, usually the prices go up. If there's large ending stocks, the prices are forecast to go down. But by and large, you can see that the production of soybeans is growing over time, and about 350 million metric tons total soybeans, and from that we get about 260 million metric tons of soybean meal, the difference being the oil that's extracted. And about 25% of all poultry and pig feeds currently is soybean meal. So it all starts with the bean. But the topic really is not soybeans, but in order to understand the variability of soybean meal, we have to understand a little bit about the bean. And we get about the bean contains about 36.5% crude protein, contains all the 8 to 10 essential amino acids. We've got about 30% or more carbohydrate. We have 50% soluble, 50% insoluble. Quite a bit of that is sugars and oligosaccharides. And then we've got fat, roughly 18 to 20% fat, some ash, and 8 to 10% moisture in the typical soybean. And here we see, and this is US material. This is some data that was reported from the University of Minnesota. And every year they collect soybeans from around the US and do a survey. And here we have soybean production, and we can see from the last 30 years it's steadily been increasing. And we can see that the soybean yield, how many tons per hectare that's taken off of the field, is also increasing. And that's where the farmer makes his money, is from increasing yield. And typically the farmer doesn't really care anything about protein content or amino acids or anything. He wants yield. So what's happened to the protein content over time? It's gone down. Part of that is due to the increased yield, and part of that is due to the fact that the production in the industry is moving further and further north, and the farms that are in the northern territories where it's not as hot, those varieties of beans yield less protein. And then on average, the soybean oil is pretty flat. It's not really affected. But as we know from being a poultry nutritionist, the poultry really don't grow on protein either. They grow on digestible amino acids. So anyway, over the last 30 years, about a 1.5% decline in crude protein. So let's talk about the amino acids. So on the x-axis we have crude protein from about 30% to 50%. And we have each of these essential amino acids there. Lysine on the top, and we have the amino acid content of the whole soybean. So as the protein of the whole soybean goes up, of course the amino acids should also go up, and that's what we see there, and lysine is the steepest one. But if we look at the amino acid as a portion of the crude protein, we can see that as the protein goes up and up and up, those amino acids that are contained in that protein actually come down a little bit. So if you have a really high protein soybean meal, the percent of that protein that's lysine may be a little bit lower than a lower protein soybean meal. Am I on echo now? Can sing Caro okay. The other thing to keep in mind, in the typical feed, whether it's a poultry feed or a pig feed, roughly 50% of the price of that feed is due to soybean meal. So that's a pretty significant portion of the cost of the feed, and that includes everything from the added amino acids and vitamin premix and the grain and oil and everything else. And we know that compared to any of the other so-called alternative protein sources, soybean meal is the industry standard. It's very high in lysine, around 3%, ranging from 2.5 to 3.5. It's moderate in energy, depending on how you calculate that or how you measure that, 2250 to 2600. It supplies both energy and amino acids, so if you're creating a dehulled soybean meal by removing some of the soybean hulls, yes, the protein will go up, but also the energy will go up. And you get about 15 to 25% of the metabolizable energy in a broiler diet from soybean meal in a typical formulation. Soybean meal is a processed product, and we heard the first talk today talking about processed products and controlling variation. Well, this is also a processed product, so theoretically the variation should be able to be controlled, at least that is related to the processing. The processing denatures the anti-nutritional factors, mainly the trypsin inhibitor, and also there's some other proteinaceous compounds in there and other things like lectins and allergenic proteins that may also be denatured. I've been doing some work with reduced protein feeds, and I can tell you that it's really not that easy to formulate a feed without soybean meal. You can do it, but it's very, very tricky. Soybean meal quality is variable, and we have the three main origins of soybean meal in the world: US, Brazil, Argentina, and probably the next one would be India. So we get a lot of different variability because of the processing and also because of the bean itself. So the meal is sold on moisture, crude protein, ash, and crude fiber, but the disconnect is that the chickens really require digestible amino acids and metabolizable energy to get growth rate and feed conversion. So why do we want to pay attention to variation? Well, poorly defined ingredients or ones that are highly variable are difficult. Variation in feed composition increases risk, and what we want to do is avoid oversupplying nutrients or overformulation, and we want to avoid underformulating, because either one of those is not a good situation. We either get higher costs and underutilized nutrients or poor performance. And So what we really need to do is measure the stuff, and we need to know how to measure it so we can analyze it, and we need to know how to take the sample so we can measure it. So one of the key steps is sampling. Once we get the sample, we'll talk a little bit more about that in a minute. Then we can analyze it for response variables of interest, like the proximate analysis, protein, fat, fiber, ash, nitrogen-free extract. We can look at total amino acids, which are fairly easy to analyze, not so easy to analyze the digestible amino acids. Digestibility of energy, metabolizable energy, and then we have some other quality factors that people often use, like Urease index as a measure of processing, KOH protein solubility as a measure of processing, and some other ones, PDI, protein dispersibility index, trypsin inhibitors, and some of these other ones that are a little bit more difficult to measure. And the other point I'd like to make is that if you're talking about soybean meal, then that set of quality parameters may be applicable for that, but you cannot take those optimum numbers and apply those to something like soy protein concentrate or full-fat soybean meal or soy protein isolate. So those will have their own optimum numbers. So here's some of the operations adding variation to soy products. The crop itself, harvesting, transportation, the crushing process, and the type of soy product that we're producing. And then the variables involved in the crop are the agronomic traits. We've heard a lot of that with some of the previous talks with the grains. The maturity, the type of genetics, nutrient composition, humidity, storage and transport. I've got a few photographs of that later. And then when we're talking about the crushing, there's some differences that are inside the crushing plant, whether or not the crushing plant has an expander that they use after the flaking procedure to help the oil get removed from the hexane. So that's pretty important, and many crushing plants will have an expander, but they won't expand 100% of the flakes going into the solvent extraction. And if you start talking to the people in the crushing industry, they really don't like to share a lot of this stuff with their customers. They'd rather keep that a secret. So, and then talking about variation in handling of the beans, you can see some differences here. So which one do you think would be potentially a better soybean meal? From beans stored this way or that way, or beans stored in silos with aeration? So sometimes in certain places, if you have a bumper harvest, you need to store the beans somehow instead of leaving them in the open ground. But if you put them in these silage bags and you get bad weather, then bad things can happen to those beans. Oops. Then you have inside the crushing plant, this is the desolventizer toaster here, and many different types of meal can come out of the different types of crushing plant. So I've just got some photographs here. That would be a press cake. That would be an example of partially over-toasted soybean meal. I'm not sure if we see this much anymore, but it used to be that most of the meal from Argentina came in pelleted form. Do we still see the pellets? Yeah, so that's different. A lot of things can be hidden in those pellets that you really can't see when you get the meal. But they do that to improve the shipping characteristics. And then we've got a soybean meal that contains some soybean hulls here, you can see. And then a better quality soybean meal with less hulls. And then a really, really good high quality soybean meal that's very uniform and hardly has any soybean hulls. So just looking at the pictures, you can guess that you might get, different performance if you fed different types of meal. But if you buy the meal, you buy it on specifications. And these are the official specifications from the U.S. National Oilseed Processors Association. Is there a Brazilian Oilseed Processors Association? No. Is there an Argentina one? No. India has one, but anyway, so if there's two types of meal here, dehulled and not dehulled, and you have a different set of specifications there. You talk to your trader, you tell them what you want. You want high protein meal, low fiber meal, moisture content, and then you sign the contract. Unfortunately, this has nothing to do with the amino acids, energy, amino acid digestibility, or variability of what you're getting in that shipload. Here's a slide showing some data when I lived in Singapore, and we took one sample of soybean meal and we ground it in a Retsch laboratory grinding mill. And we ground about 15 kilos of this stuff and took the output, mixed it up very uniformly, and put it in small sample jars. And then I called different laboratories, and this happens to be Indonesia, Malaysia, Singapore, Thailand, Philippines, and one company in Vietnam. And we said, we're going to send you some soybean meal sample. Please analyze it for moisture and crude protein and anything else you can analyze it for, and send me the result back. And then we'll send you another sample. But we didn't tell them that we're going to send them the exact same sample. So the idea was to send each lab the exact same sample over time, 8 different times. And these are the numbers we got back. And these are all adjusted to 12% moisture. So you can see here, crude protein. What's the crude protein content of that soybean meal? Is it the high one, the low one, or what? So, not only are you dealing with variability of the stuff that you're buying, you're also dealing with a lot of variability within your own lab from here to here or across different labs. So it's very difficult. So the take-home story from this is, if you're relying on your own company laboratory, that you should make sure that that laboratory has external testing and is on a check sample program, and just rely on one lab to formulate your feed, not several different laboratories. So these are some of the specifications. You'd preferably like your total lysine to be more than 2.8%, your ash to be less than 7.5%, silica less than 1%. And then we've got protein solubility and 0.2% potassium hydroxide. Probably the higher the number, the better there, because that represents higher digestibility, as long as you've knocked out some of the trypsin and most of the trypsin inhibitor. So this one is not an easy thing to measure. I think it's a 22-step procedure. So the thing that's easy to measure is urease activity. And that can be measured 2 different ways. One way is looking at the rise in pH. You put some urea with the soybean meal. The enzyme present in the soybean meal will convert the urea to ammonia, and the pH will go up under controlled conditions. Or you can measure how much nitrogen is released from the urea over a period of time. That's the EEC method. So then you've got 2 different methods. You've got the American method and the European method that may not give exactly the same results. So here's a test of a bunch of different soybean meal samples that were tested with the European method, nitrogen release per gram per minute, against the delta pH method. And you can see in the lower area, when the urease activity is low, they're fairly close to one another. 0.4 is about 0.4. But as you get to more and more under-processed soybean meal where the urease activity is higher, then those scales diverge. So you really need to be aware of that, which procedure you're using, and use the same procedure every time to avoid having analysis laboratory variation. I probably should have showed this first, but this just shows the protein and amino acid digestibility reaching a maximum at an optimum, under optimum processing conditions of heat, moisture, and we can see the heat labile anti-nutritional factors, mainly the trypsin inhibitor, they start going down, down, down. If you get it too low, then you're over-processed and you've denatured the amino acids that you need to grow the chickens. So here's all these tests we can run: trypsin inhibitor, urease, KOH protein solubility, PDI, and lysine as a percent of crude protein. And back a few years ago, this was the one that everybody seemed to really use and rely on quite a bit. The problem with that one, you saw the crude protein values across the different laboratories were really variable. This thing is like super variable if you test it between labs, or even test the same sample in the same lab different times. So it's been thought that the lysine as a percent of crude protein is probably a better value to use. Would you agree with that, Jan?
In order to measure heat damage,
Yeah, so that we're talking on the high end of the scale, the heat damage. On the lower end of the scale would be the maybe the trypsin inhibitors. So we'll go back now. I mentioned earlier about sampling variation, and you can see the guy in the picture there. That was probably 15 years ago. He looks exactly the same now, so he hasn't changed a bit. Some of us have gotten a lot fatter over the years, but Ferry's the same. We have to keep in mind how we sample our product, because if the sample you get is not a good sample, then no matter what you do to it in the lab is not going to make any, is not going to help you. It's like garbage in, garbage out. So we need a nice long probe that we can get a nice cross section in whatever container we're sampling, and we need to get a large enough sample and put it through a riffler or a Borner divider to reduce the sample. And it's amazing, working at the university, you tell the student, all right, we're running this feeding study, get a sample of the product because we have to analyze it. And they come back and they just grab, a handful off the top of the bag. How did you get the sample? I just took a handful off the top of the bag. No, you have to get a cross section of the bag and get a very large sample and then evenly cut that down and send that to the lab. And if you're talking about commerce, we've got grain, we've got an organization, GAFTA, which is the Grain and Feed Trade Association, which is from the UK. They develop all these contracts. About 80% of the world's grain is traded under GAFTA type of contracts. In the US, you have National Oilseed Processor contracts, NOPA contract, and you can write whatever you want in the contract, and that's between you and the company you're buying the raw material from. But they also have published sampling rules of how to get the samples and how those samples are taken for analysis. And I just want to explain this because it's pretty important. In the big ports where they're filling the ship with material, usually the contracts are written the quality at point of loading. So if the thing is loaded in the US in New Orleans and it's sent to Poland to be unloaded, you're stuck with the analysis at the point of loading. Whatever it is when it gets here, that's not the seller's fault. That's your fault and the shipping company, between you and the shipping company. So at the point of loading, they have automatic sampling devices, and they keep samples of the various lots that go into the ship, and those are analyzed before that lot goes into the ship. And so depending on the size of the ship, let's say this is a 0 to 5,000 metric ton ship, each lot size will have to be at least 500 metric tons. You need to have at least 20 samples from that 500, and each of those samples, the aggregate needs to be consist of 20 kilos a sample, and then that's cut down evenly, and you end up with a 1 kilo sample. And as the size of the ship goes up, here's greater than 25,000 tons, you have more samples and larger samples. So depending on how you organize the shipping contract will tell you how uniform that grain is by the time it gets to you, or the soybean meal. So there's some different ways that you can write the contract, and one of them is something called the cumulative summary. So that as that ship is being filled, each of those sublots are measured, and you can write it that with the CuSum, and that means that it accumulates the variability over time. Each point is either in or out of control. So if it's out of control, it'll be rejected. And that's designed to be reasonably ensure that no factors of the ship lot exceed the grade limits. And that will ensure a certain degree of uniformity. So here's if you just say, I want average of 48% crude protein in my soybean meal. You're going to get some sublots that are maybe 42%, and there's off balance by some perhaps higher numbers. Or you can say, and most people don't do this because it costs too much money, I want no sublot to be less than X amount of crude protein, or no sublot to be more than X amount of crude protein. Or you can do this cumulative sum contract where it's kind of a running total as you go, and it's somewhere in between the average and not more than or not less than. So a lot of variation can be controlled by how you write the contract for your incoming raw materials. And then you got to keep in mind, once that thing's loaded onto the ship, it's no longer in the selling trader's hands anymore. He's out of it. So now it's between the buyer and the shipping company. And so some problems in some of these ships, you have heated fuel tanks. So they're trying to keep the bunker fuel warm so it doesn't get, kind of like driving a diesel car in wintertime, it can freeze up. So they put heaters in there. And if you get your grain or soybean meal in one of these compartments that's next to the heaters, that can drive all the moisture away from the material, and then it starts condensing, and once it condenses on the other side, you start getting mold growing, which creates more moisture. And then that ship gets to the destination port, and they open up the cargo hold, and it's a bunch of rubbish, and there's a big problem. And here's another picture from Thailand, and that's exactly what happened to them. And so the results can be disastrous and a lot of unhappy people. So something to be just aware of. And it does get moldy. And then once you get it to your feed mill, how are you going to control the variation? Well, perhaps you're not going to store it in an open sort of storage system like this, because not only would you have nutritional variation, you get some biological variation, salmonella and everything else that can be a big problem. How am I doing on time? Okay. So it's all a statistical game. So understanding and managing the variation is about statistics. We can't know the true meaning of everything, but we can manage the uncertainty. So you have to think in terms of probability. And I'd just like to show a series of slides from different sources. This is again from the University of Minnesota showing soybeans, 636 US, 645 Brazil, and 424. And I've got this as the average plus the, and then the coefficient of variations in the parentheses there. And I like to see the coefficient of variation more than the standard deviation, because the standard deviation, it's hard to look at that number and compare different sources. You have, the CV is a standard deviation divided by the mean times 100. So what you can see here, the crude protein in the US is a little bit lower, the variation is a little bit lower. The 5 essential amino acids, a little bit higher in the US, and the variation's lower. The next, that's beans. The next set is soybean meal, and this is some meta-analysis done by Gonzalo Mateos from Madrid, and he's examined soybean meal samples from research publications, peer-reviewed research publications, 417, 381, 454, and 84 is the N. And again, you see the crude protein a little bit lower in the Argentina, and next would be the India and the US. And then these also were examined for the carbohydrate content, or at least the sugars and oligosaccharides. And we can see here that the sucrose content of the US meal appears to be higher than the other forms. Probably next would be the Argentina, because the varieties would be similar between those two countries. And the crude fiber is the lowest in the US there. Next one is amino acids, the same group of samples from those publications. And we can see that the lysine content there looks to be the highest in the US sample and the lowest in the Brazilian sample. This is some data from Garcia and Rebolar, and they've looked at 170, 165, and 180 from the different origins, and looking at some of these quality parameters. So we can see that, let's look at the trypsin inhibitor, looks to be a little bit higher in the US meal compared to the other ones, but if it's under about 4, it should still be good. And then the heat damage index, which is an NIR technique, the lower the number, the better. So even though the trypsin inhibitor is a little bit higher, the heat damage index is low. And then another one, this is showing the KOH protein solubility across 3 different laboratories. And each one of those is a sample of full-fat soybean meal. And you can see why the KOH protein solubility may not be that wonderful of an assay. Might be good if you have an experienced technician and you're doing it the same way in your own laboratory all the time, but if you're sending the sample out to another laboratory, you may get completely different numbers here. So that gives a little less certainty to that technique. And then these are different assays that can be done on soybean meal. showing the coefficient of variation. Very low for dry matter, very low for crude protein, a little bit higher for ash, but all these other ones are really, really high in variability. And, but luckily the CVs for essential amino acids are quite low. So they seem to follow the crude protein. And look at the urease over here, 201% CV, so that's really not a very good assay to use. And here's some data from many, many samples, 74,880 that were analyzed by NIR at Advancia. And within the normal range of soybean meals would be between, let's see, this is total lysine as is and digestible lysine. So the higher the total lysine, the higher the digestible lysine, and but there's quite a lot of variability within there. And then they've got some samples way down here at the bottom, which sort of are involved in the regression there, but probably shouldn't be because they're sort of outliers for commerce. So in conclusion, there's variability in soybean meal, and that can be caused by bean genetics, bean storage, how the material is processed, and a lot of it has to do with sampling variation. So you really need to get a good sample and measure it in a good laboratory to be assured of what you really have. Laboratory measurements can be variable, but variation can be controlled using the NIR, and that's a rapid secondary technique that we'll probably hear more about because Advancia is very involved with their precise nutrition arm of the company using NIR to analyze raw materials, and that can really help. Variation can also be controlled at purchasing and how the purchasing contracts are written. And with that, I'll end it. Thank you very much.